In the first week of class, we covered magnetic induction, and last week we looked at alternating current, and that all led to this week, which is inductance in AC circuits. So we learned that when current flows through a conductor, a magnetic field is created. So in this case, this is a conductor here, and we have an AC, an alternating current, flowing through this conductor. And all this slide is showing is that the magnetic field is expanding and collapsing. We'll cover this more in more slides, but that's just the basic concept for right now. So here we see we have this is an AC power supply. It's AC because it has this little sine wave in there. And it's connected in a circuit this is an inductor. So this coil of wire here is an inductor. It's literally just a coil of wire. And we have a complete path that goes all the way back to the power source. And this is showing that during this part of the AC voltage, the rising part of the voltage, it's showing that the magnetic field is expanding. On this side, the AC voltage is decreasing, it's going down to zero, and we have a collapse of the magnetic field. So in this slide, we have again an AC power supply here. It's connected in this circuit that has a coil wired in series. We have a complete circuit that goes all the way back to the voltage source. And so we have the applied voltage that's coming from the power supply. And we learned that we get an induced voltage when we have current going through a coil. What this slide is showing is that the applied voltage and the induced voltage are out of phase with each other. They're out of phase with each other. And in fact, they are 180 degrees out of phase with each other. So here's our typical XY graph. We're measuring voltage against time. And here we have the applied voltage. And we see that the induced voltage is exactly opposite in polarity of the applied voltage. These two voltages are 180 degrees out of phase. That's what this slide is showing. This slide is kind of interesting here. So on this side, we have an ohm meter here. And we have this coil of wire, literally just one piece of wire that's coiled around this, whatever this core is, and we're measuring the resistance of that wire. We know that copper and aluminum conductors have a little bit of resistance, and we're measuring that resistance. Okay, now we switch over to this side. Now we have 120 volts AC applied to the same coil, and in series we have a current meter, an ammeter. This is measuring current. So we're applying 120 volts AC. We're going through this coil of wire, and we learned from this side that we have 6 ohms of internal resistance, and we're measuring 0.8 amps. Now we know from Ohm's law, you covered this in DC fundamentals, that current equals voltage over resistance. So we have 120 volts divided by 6 ohms. And normally what we would think we would get from this math is 0.8 amps, because that's what the ammeter is reading. But if we do this math, we get 20 amps. So the math tells us that we should get 20 amps, but the actual current meter is saying we're getting 0.8 amps. So the reason there's a difference is because of the induced voltage that is out of phase with the applied voltage. So if we approach this from a different angle, and we instead think about, okay, how much voltage do we need to push 0.8 amps of current through the 6 ohms of resistance? So we go back to Ohm's law, and we know from DC fundamentals that voltage equals current times resistance. We're trying to figure out how much voltage do we need to get 0.8 amps to flow through 6 ohms of resistance. And what we get is 4.8 volts. So we're applying 120 volts, and basically we're using 4.8 volts of that to push current, and all of the rest of the voltage, the applied voltage, is used to sort of overcome the induced voltage that's induced in this coil. There's a formula that we can use. It's in the textbook. I won't cover it in great detail, but we can actually calculate the amount of induced voltage, and it is the square root, in this case 120 volts squared, minus 4.8 volts squared, and the induced voltage is 119.9 volts. This will make a lot more sense when you read the chapter and as we go through these slides. So we know that from the last slide that the inductor, the coil of wire, it's limiting the amount of current that's going through the inductor. That current limiting property, that's called reactance. And we're going to be looking at reactance a lot in this course. Now, given that we're talking about inductors and inductive loads and so on in AC, we in fact have inductive reactance. The symbol for inductive reactance is X sub L. L is the symbol for inductance. X is the symbol for reactance. The unit of measurement for inductive reactance is ohms. Now, we use ohms because it's a current limiting thing, as I like to call it. Inductive reactance is not resistance. So keep that in mind as we go forward. And we know from previous classes that induced voltage is determined by the number of turns of wire, how strong our magnet is, and the speed of the cutting action. This is a very simple slide. This top inductor literally has more coils of wire, so it has more inductance. The bottom coil, the bottom inductor, has fewer coils of wire, so it has less inductance. These are just some different symbols. If we were in a normal class setting, I typically use just a simple coil. If we have, or just a simple looped line, so to speak, I use this symbol all the time. But there's also inductors that have cores in them. And if you watch that other video in D2L before this one, you'll understand what the cores are. But this slide is just for different symbols. We can wire or connect inductors in series. We know that this is a series circuit because we have one current path. And when we do connect inductors in series, we simply add up the individual inductances of the inductors to get total inductance. Inductive reactance, again, that's the current limiting thing. It's actually X sub L total. I like this way of writing it rather than this way of writing it. The inductive reactance, the total inductive reactance, is literally the individuals added up. So total inductive reactance. We can also wire or connect inductors in series, in parallel. We know that this is a parallel circuit because we have multiple current paths. And very similar to resistance, if you recall from DC fundamentals, the total inductance is the sum of the reciprocals of all the inductors. I'm going to again point you to Appendix B. It might be a different appendix in the 7th edition, but in the 6th edition there's Appendix B, and that has all of these formulas in there for all of the stuff we're doing. Open book, open textbook quizzes and exams, so please use your textbooks and use Appendix B. It's actually a really wonderful resource. So we saw earlier that applied voltage and induced voltage are 180 degrees out of phase. We're now looking at, in this, we're comparing the current flowing through a circuit compared to the induced voltage. What I want you to remember is that current lags voltage by 90 degrees. In particular, lags the induced voltage by 90 degrees. Because we know that the applied voltage and the induced voltage are 180 degrees out of phase, the current leads applied voltage. So circuit current leads applied voltage by 90 degrees. Current lags the induced voltage by 90 degrees. Current leads applied voltage by 90 degrees. What this graph or this slide is showing is that so we have the relationship of, so here we have the induced voltage and we have the circuit current. And we see that they're 90 degrees out of phase. And what this is showing, so this 0 point right here, this is 0 volts because this is the induced voltage curve. This 0 volts corresponds to this point on the current curve. At this moment in time, this exact moment in time, current is not changing. As it's going up to that point, it's increasing, it's increasing, it's increasing, and it's steady just for a moment in time, then it turns around and goes back negative. That moment in time, the current value is not changing. Current is still flowing, but the value, it's not increasing or decreasing. Because there's no change in current, there's no induced voltage at that moment in time. That's what this slide is talking about. So if we look at a different point here, so we're again looking at the voltage curve right here. We have this maximum negative peak, and it corresponds to this point in time on the current curve. And at this point in time, the rate of change of current is maximum. So the rate of change of current is maximum, so the voltage is maximum. Here we have the same thing. Current is going down, and we get the maximum induced voltage at the same moment in time of the greatest rate of change of current. So power in an inductive circuit. This I found is sometimes difficult for students. So no true power as measured in watts is produced in an inductive circuit, in a purely inductive circuit. There is no actual true power. This will make more sense when you read the chapter, but it's because of the relationship between current and voltage in an inductive circuit. Because they're out of phase with each other by 90 degrees, when it comes to power, and power equals voltage times current, basically they're kind of canceling each other out. We have, I'm guessing this is voltage and this is current. We have them positive together, so we have this sort of little triangle of time, but that's being canceled by this little triangle of time, and vice versa for all the other points. My point is they kind of cancel each other out, and the net point here is no true power, no wattage is produced in a purely inductive circuit. Power in an inductive circuit is not true power, it's reactive power. And instead of using watts, which is the unit of measurement for true power, we have volt amps reactive, or VARs. And you'll notice here that these different equations and formula for VARs correspond to what we see in the power wheel or in Ohm's law, but instead of using resistance, for example, we're using inductive reactance here. For this one, we're using the current flowing through the inductor and the voltage across the inductor. Here, same thing here. It's all in through the inductor and inductive reactance. The Q of an inductor is basically the quality of the inductor, and it's basically the relationship between the internal resistance of the coil, and by that I mean the actual wire that's used in the coil. That actual wire has some internal resistance, and it's very small, but it's there. And so quality, we have a formula here, again, Appendix B, is simply inductive reactance divided by that internal, this is that internal resistance here. Usually this number, this Q, is something very big, and that's because inductive reactance is much, much, much greater than the internal resistance. But what we're looking for here is we want Q to be greater than 10. If it's greater than 10, then the inductor or the coil is said to be a quality inductor. In reality, this number is actually much, much larger than 10. So here we're comparing two different coils. This one here, this is a large gauge wire. So let's call this, I don't know, let's just make it up. This is an 8 gauge wire. Versus this inductor down here, it's a small gauge wire. Let's call it 14 gauge wire, for example. The size of the wire, the gauge of the wire, affects the Q, or the quality of the inductor. Large gauge wires have a higher quality. Small gauge wires have a lower quality. This slide is showing sort of graphically the relationship between inductive reactance and resistance. When we combine those two, we get impedance. We can think of impedance as sort of the total current limiting things in a circuit. Now, because the current and the voltage are 90 degrees out of phase, and all of the different things we looked at in previous slides, the resistance and the inductive reactance are not simply added up. We have to do some math to get the impedance, and that math is actually shown quite well in the textbook. This is just sort of showing graphically the relationship between inductive reactance and resistance, and how it leads to impedance. This is very similar. So in summary, when we have a change of current, we get induced voltage. In fact, the induced voltage is proportional to the rate of change of current. And we know that the induced voltage is 180 degrees out of phase with the applied voltage. Inductive reactance, that's the current limiting thing that inductors or coils produce. It is measured in ohms. And you won't be tested on this, but it is proportional to the inductance and the line frequency. Actually, my apologies, you will be tested on this. We're going to see this later, but I'm jumping ahead. Inductive reactance equals this, it's this formula. I'm just, again, I'm jumping ahead, but inductive reactance is proportional to frequency and inductance. 2 is it's the number 2, pi is 3.14, so it's just a number. So you will, I apologize, you will be tested on this, but we'll get to this. Don't worry about it for now. Inductance is measured in henries. We can connect them in series or in parallel, and we have different math. Appendix B will give you the correct math. This is an important one here. Current lags. Current and voltage are 90 degrees out of phase. And when you read the chapter, and we can discuss it more on our WebEx session, but current lags applied voltage, and current leads induced voltage. All inductors have some amount of internal resistance. That's the actual resistance of the wire, and that allows us to calculate the quality of the inductor, and we're looking for Q to be 10 or higher. In a purely inductive circuit, we do not have true power, we have reactive power, and it's measured in bars, volt, amps, reactive. And that ends the chapter.